In this video, we're going to see how to solve second-order linear differential equations. In particular, we're going to focus on ones that are constant coefficient, and you can write them down as ax double prime plus bx prime plus cx equals some known function f of t that's given to you in the problem. And really, for our sake, our f of t is generally going to be 0. It's going to be what's called a homogeneous differential equation. And I'll make a mention as to what's going to happen if it's not. But if we look at homogeneous equations where the right-hand side equals 0, we're going to take our differential equation and turn it into a polynomial. This is called the auxiliary equation or auxiliary polynomial. Basically, for every derivative you have, you replace it with a power of s. So x double prime becomes s squared, x single prime becomes s, and x with no primes, it just goes away, and we have our coefficient. So we get as squared plus bs plus c equal to 0. Now at this point, you can either factor it sometimes, or failing factoring, you can use your quadratic formula. And I don't want to call S1, S2 just yet. It would be S is negative b plus or minus the square root of b squared minus 4ac all over 2a. And because of the plus or minus, you're going to get two answers. Now, if you get two answers that are different and they're both real, so you don't have to deal with imaginary numbers at all, then that's what we're going to call case 1 here. So again, if you really wanted to write it out, it would be S1 is negative b plus the square root of b squared minus 4ac over 2a. And then S2 would be the minus square root here. You don't really need to write it out separately like that, but this is going to be our two roots. And when you have those two roots, then you can write down the answer to them. The answer is going to be x of t is some constant k1 e to the s1t plus some constant k2 e to the s2t. So when we solve for our s values, those are going to be the numbers that are in the exponential function e to the number times t. So that's what happens when you have two different real roots. Now if you happen to solve it, and the square root part becomes 0 there, that means you have a repeated root. So your root is just going to be the negative b over 2a, and it just happens twice here. And if that's the case, then the solution for the differential equation is going to be x of t is some constant k1 e to the s1t plus some constant k2. And since there's no second power we can do, we have to have the same power. But if all I had was the same power, you can combine them together. So what ends up happening is you're getting an extra t involved. So it's t e to the s1t. And you can prove mathematically that you're going to have to multiply by t there, but for now, we'll just take it as a given. That's how we get our second answer there. Then when I do case 3, this is where when you take the square root, it's the square root of a negative number. And so we just rewrite this here, this negative b plus or minus, the standard differential equation here. We rewrite this as alpha plus or minus beta times I. Right, so alpha is the real part, beta is the imaginary part. And when you have this case, it turns out using something called Euler's identity, you can rewrite this as some constant e to the real part alpha t times cosine imaginary part beta t. And then for your k2 term, you have the same e to the alpha t, but this time you get sine of beta t. So the three situations are if you have two different roots, you have two different exponential terms. If you have a repeated root, you have an exponential term and t times an exponential term. And if you have two complex roots, then you have one term with e and cosine and one term with e and sine. Now, for the particular solution is if it's not homogeneous, if the right-hand side is some other function, well, the particular method would depend what the right-hand side is, but for us, our right-hand side is always going to be a constant. And what that means is my particular solution is also going to be a constant. So then my final solution for case 1 is going to be x of t is k1 e to the s1t plus k2 e to the s2t plus some constant c. My case 2 is going to be k1 e to the s1t plus k2t e to the s1t plus some constant c. And my case 3 is x of t is k1 e to the alpha t cosine beta t plus k2 e to the alpha t sine beta t plus some constant here. And just in general, just so you know on these, because of the physical nature of these circuits and what we're talking about, all these exponentials are going to have negative exponents, which means as you go to infinity, all the exponential parts are going to go to 0. So this plus c here, it's always going to equal the value of the function you're looking for at infinity. So part of our analysis of circuits is going to be what happens as you go to infinity, what is the value of the thing that we're looking for at infinity, and that will tell you what your plus c value is when you're solving these equations.